Ever stop to marvel at the hidden activity inside your computer?
Hmm.
I mean, you click an icon, send a message, watch a video.
Uh-huh.
These everyday actions seem so simple, yet they rely on, well, a staggering level of intricate design humming away beneath the surface.
Totally.
Even the most basic operation is this carefully choreographed dance of tiny components.
It's a perspective we often lose,
Yeah.
especially in today's world of high-level software development. We
Mhm.
work with these powerful languages, operating systems. It's easy to forget the actual machinery that makes it all possible.
And that's exactly what brings us to this deep dive.
Hmm.
One of you, a wonderfully curious mind, shared Randall Hyde's Write Great Code, Volume 1, Understanding the Machine.
Ah, HYDE. Good stuff.
Now, this isn't your typical coding manual. Think of it more like a backstage pass to your computer,
Mm-hmm.
revealing everything from the raw representation of numbers to the intricate details of how data gets in and out. It's substantial, big read, but packed with fundamental insights.
Yeah, HYDE's core argument really is that to truly write great code, not just functional code, but efficient, robust code, you need to grasp how the abstractions,
Right.
the things in your programming language, translate into the low-level capabilities of the hardware. It's about knowing the machine intimately.
So our mission today is to unpack this rich source material. We want to extract the key insights, the fundamental principles of how a computer system operates.
Sure, distill it down.
Exactly. Give you a shortcut to understanding the machine that powers your code without, getting lost in every single technical detail.
Mm,
Okay, let's unpack this. Starting with something truly fundamental, how computers understand and manipulate numbers.
right. And at its core, it all comes down to binary, the language of zeros and ones.
The absolute bedrock.
Yeah, we humans were comfortable with decimal base 10,
Mm.
but computers, they operate using base 2. And HYDE explains that understanding binary directly shows you the fundamental limitations and capabilities of the hardware.
Like why powers of 2 pop up everywhere.
Exactly, why they're significant in memory allocation or bit manipulation. Converting from binary to decimal, well, it involves recognizing that each position in a binary string represents a power of 2.
Uh-huh.
A 1 in that position means you add that power of 2 to the total. Simple as that, fundamentally.
Right. Like take binary 11000010. That's 1 times 2 to the 7th plus 1 times 2 to the 6th, 0 times 2 to the 5th, and so on.
Mm-hmm.
Adds up to 202 in decimal. And going the other way, decimal to binary, that involves repeatedly dividing by 2, right? And keeping track of the remainders.
Yep, that's the standard algorithm. Now, while binary is the machine's native tongue, long strings of zeros and ones, they can be difficult for us humans to read and work with.
Oh, definitely. Error prone.
Exactly. That's where hexadecimal, or base 16, comes in handy. Each hex digit neatly corresponds to exactly 4 binary bits.
Ah, the 4-bit chunks.
Right, which makes it a much more human-readable way to represent binary data. Think of it as a convenient shorthand. Converting between hex and binary is super simple. Just substitute each hex digit with its 4-bit binary equivalent and vice versa.
Exactly. So hex ABCD just becomes 10, 10, 10, 11, 1100, 1101 in binary. Way easier to scan than that long string.
Much easier.
And it's useful to recognize these conversions because even though our high-level languages handle it automatically,
Most of the time, yeah.
understanding this underlying process helps you appreciate what the computer is doing.
Yeah.
Especially like when you're debugging or looking at low-level system stuff. HYDE also points out how different languages represent binary values, maybe with prefixes like percent or 0b, or sometimes suffixes like b.
Yep, these conventions. He then moves on to the concept of bit strings and their common sizes. You've got the nibble,
The 4-bit one.
that's the one, 4 bits, then the byte, the fundamental 8-bit unit,
Yep.
and often the smallest addressable chunk of memory.
Okay, that's key. The smallest thing you can point to directly in memory is usually a byte.
Usually, yeah, on many systems. Knowing this immediately tells you why you often deal with data in multiples of 8 bits and, the potential overhead if you're storing smaller things.
Right.
Then you have the word, typically 16 bits, double word, or word, 32 bits, quad word, 64 bits, and even long word, 128 bits, though that's less common maybe.
But the byte being the smallest addressable unit that really sticks.
It's a crucial takeaway. It really puts into perspective how data is organized at the most basic level and why certain data sizes are just so common in programming.
Okay. Now, beyond just positive whole numbers, computers also need negatives. And HYDE explains that most systems use 2's complement for these signed integers.
Yes, 2's complement. It's a really clever system, actually. It allows for efficient arithmetic on both positive and negative numbers. using the same circuitry.
The same adder does both.
Pretty much, yeah. The beauty is you can use the same adder circuit for both addition and subtraction, which simplifies the hardware design quite a bit. So it's really crucial to understand the distinction between signed and unsigned numbers.
Because it changes the range.
It affects the range of values a given number of bits can represent, absolutely, and also how arithmetic operations behave. An overflow means something different for signed versus unsigned.
And when you're dealing with numbers of different sizes, you hit these concepts like sign extension, zero extension, and contraction.
Right. Sign extension preserves the sign, the positive or negativeness of a signed number when you move it to a bigger container, like from a byte to a word.
Okay.
Zero extension just adds leading zeros when you do the same for an unsigned number. Simple enough.
But contraction, that sounds risky.
Contraction is the risky one. That's when you try to fit a larger value into a smaller representation. And as HYDE warns, this can definitely lead to data loss.
Right, you just chop bits off.
Sometimes, yeah. Programmers need to be really aware of this. Some languages might just lop off the extra bits, maybe with a warning, maybe silently. It depends.
Yikes. Okay.
Finally, in this number representation area, HYDE touches on scaled numeric format.
Scaled numeric.
Yeah, it's an interesting alternative for representing fractions precisely, especially in bases other than binary, maybe like ternary, where you could exactly represent something like 13.
How does that work?
Well, the idea is you multiply your fractional value by some scaling factor, like, say, 100 if you want 2 decimal places to convert it into a whole number.
Ah.
Then you do all your math using integer arithmetic, which is exact, and then you just divide by the scaling factor again when you need to display or output the result.
So you avoid the floating point fuzziness.
Potentially, yes. It requires custom input and output routines, sure, but the key insight here is that it offers exactness in certain scenarios where standard binary floating point or even decimal floating point might introduce tiny approximation errors.
Interesting alternative. Okay, so we've got a solid foundation in how computers represent numbers. But what about actually doing math with them? That's the next logical step, right?
Absolutely. HYDE walks us through the fundamentals of binary arithmetic, addition, subtraction, which involves borrowing, just like in decimal.
Comfortingly familiar.
Yeah. Multiplication and division, too. The core principles are very similar to what we learned in grade school, just, applied to base 2.
It's almost nice to see that even at that low level, the underlying logic is kind of the same, but then things get a bit more bitwise.
Exactly. Bitwise logical operations. NED or XOR and NOT. These operate directly on the individual bits of a number.
Okay.
And HYDE provides some great examples of their utility. For instance, you can quickly check if a number is odd, or even just by using a bitwise AND with 1.
How does that work?
Well, if the last bit is 1, the number is odd. ANDing with 1 isolates that last bit. So if the result is non-zero, the number's odd.
That's a neat trick. It really highlights how understanding the binary representation allows for these clever optimizations at the code level.
Definitely. And then there are bit shifting operations left shift and right shift.
Yeah, multiplying and dividing by 2.
Exactly. They're incredibly efficient ways to multiply or divide by powers of 2. Much faster than using the dedicated multiplication or division instructions on many processors. And related to shifting is bit rotation. That's where bits shifted out of one end kind of wrap around to the other end.
Right, they don't just fall off.
Precisely. Now, it's not as commonly available directly as a single operation in many high-level languages, but HYDE shows how you can synthesize this using a combination of shift and OR operations.
Better.
Finally, in this section, HYDE delves into packed data structures.
Packed data. Squeezing things in.
Yeah, basically. This is where you use bitwise operations and masking to squeeze multiple small pieces of information into a single larger data value, like a single integer.
How do you get them back out?
You use AND with a mask to extract specific fields and OR to insert them, often combined with shifting to get the bits into the right position first.
Right.
It's all about efficient use of memory, even if it requires a bit more manipulation, fiddling at the code level. Think of it like carefully arranging items in a suitcase to maximize space.
Okay, so it's a trade-off.
Exactly. A trade-off between space efficiency and maybe the complexity of accessing and modifying those individual fields. HYDE's examples really illustrate how these bit-level manipulations work and why they might be used in performance-critical code, or maybe when dealing with low-level hardware interfaces where data is packed like that.
Now, we've talked about whole numbers,
Yeah.
integers,
Yeah.
but the real world often involves fractions, and incredibly large or small values.
Yeah.
That's where floating point arithmetic comes in, right?
Yes, absolutely. Integers and even those fixed point formats we mentioned have their limitations. Floating point numbers overcome these by using two parts: a mantissa,
Which is like the significant digits.
exactly, the significant digits, and an exponent, which determines the magnitude, how big or small the number is, and effectively the position of the binary point. This floating binary point allows for a much, much wider dynamic range.
But there's always a but, isn't there?
There is. As HYDE clearly points out, this flexibility comes with a significant cost: inherent imprecision. Because you're using a finite number of bits, like 32 or 64, to represent a potentially infinite range of real numbers, floating point representations are often approximations. Just tiny ones sometimes, but they are there.
Which is why directly comparing floating point numbers for equality,
It is almost always a bad idea.
you check if they're close enough.
Absolutely. The inherent imprecision means you should almost always avoid if float A x float B. Instead, you think in terms of close enough using a small tolerance, an epsilon value.
So EBS is latent to Kelpsilon.
Exactly. That's a fundamental mindset shift for writing robust numerical code. HYDE really emphasizes the need to use these tolerances or error ranges when comparing floating point values. You have to account for these tiny inaccuracies that can creep into calculations.
Right.
He also briefly touches on the complexities of floating point addition and subtraction, which involves things like normalization, matching exponents, and even denormalized numbers to handle very, very small values near zero. It's a far more intricate system than integer arithmetic. Much more going on under the hood.
Okay, so we've covered numbers in their many forms: integers, signed, unsigned, fixed, floating point. But computers also deal constantly with text, with characters. How does that work at the machine level?
Yeah, this is where character encoding standards come into play. HYDE starts with ASCII, the American Standard Code for Information Interchange.
The classic.
The absolute classic. It's a fundamental standard that maps 128 characters, uppercase and lowercase letters, digits, punctuation, and also control characters to unsigned integer values from 0 to 127.
So 7 bits needed.
Exactly. Fits in 7 bits. And this standardized mapping is just crucial for communication between different programs, different devices. Think of it as a universal agreement, at least originally, on how letters and symbols are represented as numbers.
It's amazing to think that a simple A is just the number 65 to a computer.
It is.
And those first 32 ASCII codes, the control characters, those are for things like line feeds, carriage returns, tabs.
The invisible workhorses of text formatting, exactly. HYDE also briefly mentions extended character sets that go beyond basic ASCII, trying to include more symbols or accented characters, addressing the limitations of just 128 slots.
But even those weren't enough for the whole world.
Not even close. For truly global communication, ASCII's 128 characters, even extended ASCII with 256, just aren't enough. That's where Unicode comes in.
The big one.
The really big one. It's a much more comprehensive standard designed to support a vast range of characters from virtually all writing systems in the world. Unicode defines code points. These are unique numeric values for each character, spanning a huge range, way beyond 16 bits now.
Right. And the multilingual plain concept helps organize this vast set.
It does. And it's interesting how Unicode evolved, like you said. It started aiming for 16 bits, thinking that'd be enough. Yeah, exactly. When that proved insufficient, they introduced surrogate code points as a way to encode characters beyond that initial 16-bit range, the basic multilingual plain. It's a bit of a clever workaround to maintain some backward compatibility while expanding the number of representable characters massively.
And HYDE also gives that example, showing how a seemingly single character on screen, like an accented A, might actually be represented by multiple Unicode code points, like a base character E plus a separate combining accent character.
Yeah, the composition rules. Then we get into Unicode encodings, how those abstract code points actually get stored as bytes.
UTF-8 being the common one.
UTF-8 is probably the most prevalent, especially on the web. It's clever because it's efficient for ASCII characters. They take just 1 byte, same as ASCII, but it can still represent the full Unicode range using variable length sequences of bytes.
Ah, so it's backwards compatible with ASCII text in many cases.
Exactly. Other encodings like UTF-16 and UTF-32 exist too. UTF-16 uses 2 or 4 bytes. UTF-32 uses a fixed 4 bytes per code point. They're used by some operating systems, like Windows internally uses UTF-16 a lot, and some programming languages. HYDE points out that even though dealing with these multi-byte character sets can be complex, Modern programs really have to handle Unicode properly to support global audiences.
Okay. Now, these individual characters, they rarely live alone. They're usually strung together to form, well, strings.
Right. Text.
And Hyde discusses the different ways character strings are represented in memory, highlighting the trade-offs involved.
He outlines several common formats. There's the 7-bit string, where the length is kind of encoded in the high bit of the last byte. Compact, but limited length.
Correct.
Then you have length prefix strings. These store the length of the string explicitly, usually as a number right before the character data.
Makes getting the length easy.
Very easy, constant time. Then there are zero-terminated strings or null-terminated. Super common in C, C++, cat.
Yeah, the zero at the end.
That's the one. A special null character marks the end. The trade-off here is you have to scan the whole string to find its length.
Right. Potentially slow for long strings.
Can be. And finally, descriptor-based strings, like those in HLA, HYDE's own language, or originally in Java. These use a separate data structure, a descriptor, that contains info about the string like a pointer to the actual character data and its length.
More structured.
More structured, yeah. HYDE mentions how Java even changed its internal string representation later on, which could break code that maybe made assumptions about those internal details, a good reminder to stick to the official APIs.
Good advice. He also categorizes strings as static, pseudodynamic, and dynamic. What's the difference there?
It's about when their memory is allocated and if their size can change. Static strings have a fixed maximum size determined at compile time. Think fixed size buffers.
Oh.
Pseudodynamic might have a declared maximum size but can hold smaller strings within that limit. And dynamic strings can grow or shrink as needed during program execution, often using memory allocated from the heap. More flexible, but involves memory management.
Got it. And finally, in this character area, he talks about character sets, not encodings, but sets.
Yeah, character sets as in, like, collections of characters. For example, the set of all vowel characters or the set of all whitespace characters.
Okay. How do you represent those efficiently?
He explains the power set representation. This often uses a bit vector, maybe 16 or 32 bytes long, for ASCII or extended ASCII. Each bit corresponds to a possible character code. If the bit is 1, the character is in the set. If it's 0, it's not.
Clever. So checking if A is in the set is just checking one bit.
Exactly. And set operations like union, ORing the bit vectors, and intersections, ANDing them, become super fast bitwise operations. Very efficient.
Cool.
He also mentions list representation as an alternative, maybe storing the character codes in a list or array, especially useful for small sets, or if the potential character range is huge, like full Unicode, where a bit vector would be enormous.
Makes sense.
And then there's this interesting example of HYDE, a custom encoding scheme HYDE proposes. It tries to save space by remapping characters, but it might increase the complexity for certain operations. It really highlights that there are always trade-offs in how you choose to represent data balancing efficiency with ease of use.
All right, we've got numbers, we've got characters and strings, but where does all this stuff live inside the computer? Let's dive into memory organization and access.
Right. HYDE explains that the CPU accesses memory using addresses. And on many systems, like the by86 family we're used to, the fundamental unit of addressing is the byte. We mentioned that earlier.
The smallest chunk you can point to.
Usually, yes. He touches on memory banks and how wider data buses the highways for data between CPU and memory allow the CPU to fetch more data at once, like 2, 4, or 8 bytes simultaneously, speeding up memory access significantly.
Okay. And then there's this concept that always causes confusion, endianness.
Ah, yes, little endian versus big endian. It trips people up all the time.
So what is it, fundamentally?
It refers to the order in which the bytes of a multi-byte value, like a 16-bit word or a 32-bit integer, are stored in consecutive memory locations.
Okay.
In little endian, the least significant byte, the little end, is stored at the lowest memory address. In big endian, the most significant byte, the big end, comes first.
So the number 256, which is 0 by 0, 100 in hex.
Hill. On a little endian machine, memory would look like byte 0 contains 00, byte 1 contains 01.
Okay, low byte first.
Yeah. On a big endian machine, byte 0 would have 01 and byte 1 would have 00.
The opposite order, like reading left to right versus right to left almost.
Kinda, yeah. And this difference in byte order can cause major headaches when you're transferring binary data between systems with different endianness, like reading a file written on one type of machine on the other type.
How'd you fix it?
HYDE mentions that for simple types like words, you can just swap the high and low bytes. For larger types, you need to swap corresponding bytes systematically. The key takeaway is, You have to be aware of endianness when dealing with binary data across different platforms, or even within different parts of the same system sometimes, to avoid completely misinterpreting the information.
Got it. Be aware of the byte order. Another important aspect is memory alignment.
Yes. Compilers often add padding unused bytes inside data structures.
Why waste space?
For performance, CPUs are often much faster at accessing data that starts at an address that's a multiple of its size. Like accessing a 4-byte integer is faster if its address is divisible by 4.
Ah, okay, so the compiler adds padding to ensure fields line up on these optimal boundaries.
Exactly. It might mean a few wasted bytes here and there, but the performance gain from faster access often outweighs the small space cost.
Makes sense. HYDE also introduces unions here.
Right. Unions are structures where different data fields actually share the same memory location.
So only one field is active at a time.
Kind of. You can write to one field and then read from another field that occupies the same memory space. This can be useful for things like type punning, deliberately interpreting the same raw bits as different data types.
It sounds dangerous, too.
It can be. As HYDE warns, it's very sensitive to endianness because the byte layout matters completely, and it can lead to really unexpected behavior if you're not extremely careful. Use with caution.
Okay. Now, HYDE then takes us on a tour of the memory hierarchy. This is fundamental.
Absolutely fundamental. From the incredibly fast but tiny registers right inside the CPU core.
Fastest possible storage.
Yep, down through the various levels of cache, L1, L2, maybe L3, which are faster than main memory but smaller.
The intermediate buffers.
Right, than main memory, or RAM, which is much larger but slower than cache.
Where most stuff lives during execution.
Uh-huh. And finally, the slowest but largest layer. Secondary storage, like your hard drive or SSD.
It's all a trade-off, isn't it? Speed versus capacity.
Exactly. It's like that pantry analogy HYDE uses. Frequently used items on the counter, registers, less used in cabinets, cache, bulk goods in the pantry, RAM, long-term storage in the basement disk.
I like that. The cache memory is particularly interesting. How does that work?
Well, cache acts as a high-speed buffer for frequently accessed data and instructions from main memory. It works because programs tend to exhibit locality of reference.
Locality, you mean accessing the same stuff repeatedly?
That's temporal locality, yes. If you access something once, you're likely to access it again soon. And there's also spatial locality. If you access one memory location, you're likely to access nearby locations soon after.
Like reading sequential instructions in code or elements in an array.
Exactly. Think about reading a book. You read one word, then the next, spatial, and you might reread a sentence or paragraph, temporal. Cache memory works on similar principles, trying to predict what the CPU will need next and keeping it close by.
So if the CPU needs data and finds it in the cache,
That's a cache hit. Very fast access.
and if it's not there,
That's a cache miss. The CPU has to pause, go down to the next level, maybe L2 cache or all the way to RAM, fetch the data, and bring it into the cache first. This fetch usually brings in not just the requested byte, but a whole block of surrounding data called a cache line.
because of spatial locality.
Exactly. Fetching a whole line, maybe 64 or 128 bytes, anticipates that nearby data might be needed soon. But that cache miss incurs a significant delay, a latency penalty, which can really impact performance.
And HYDE describes different ways the cache can be organized. Direct mapped, associative.
Yeah, he briefly describes different cache mapping schemes: direct mapped, fully associative, and n-way set associative. These are implementation details about where in the cache a particular block of main memory can be stored. They represent different trade-offs between hardware complexity and the likelihood of cache conflicts, where multiple needed blocks map to the same cache slot.
But the key outcome for us programmers is just write code that hits the cache often.
That's the goal. Maximize cache hits, minimize misses. He also mentions the benefit of having separate caches for instructions and data, an I cache and a D cache, because code access patterns and data access patterns can be quite different.
Okay. And then we move beyond physical RAM with virtual memory and paging.
Right. This is a really clever mechanism, mainly managed by the operating system and the hardware's memory management unit, MMU. It allows the OS to make it seem like the computer has much more RAM than it physically does.
By using the disk.
By using disk space as an extension of RAM, the OS divides memory into fixed-size chunks called pages. Inactive pages currently in RAM can be temporarily moved, swapped out, to a special area on the disk.
The swap file or page file?
Exactly. This frees up physical RAM for pages that are actively needed. When a swapped-out page is needed again, the OS brings it back into RAM, swaps it in, possibly swapping out another inactive page to make room.
So RAM acts like a cache for the disk, in a way.
HYDE draws exactly that parallel. It uses the same locality principles, but he also warns about thrashing.
Thrashing sounds bad.
It is bad. Thrashing happens when the system is constantly swapping pages in and out because the active working set of memory the pages a program needs right now doesn't fit well into the available physical RAM. The system spends more time managing pages than actually running the program. Performance just tanks. It's like trying to juggle way too many balls at once.
Ouch. So how do we avoid that or generally improve memory performance?
HYDE provides some practical tips. Things like accessing data sequentially when possible, especially arrays. Grouping related variables together in your data structure so they end up close in memory.
To improve spatial locality.
Right. Using local variables, which often end up on the stack or in registers, instead of global or heap variables where possible. Sometimes separating frequently accessed scalar variables from large, less frequently accessed aggregate data structures. It's all about maximizing that locality of reference to keep the caches warm and minimize page faults.
Okay. He then outlines the different sections in a program's memory space.
Yeah, a typical layout, you've got the code section or text section for the actual machine instructions. You have constant data and read-only data sections. The static section for global and static variables that have initial values. The BSS section for global and static variables that are initialized to 0 by default.
BSS.
Block, started by symbol, historical name, just think uninitialized statics. Then you have the stack.
For function calls, local variables.
Exactly. Grows and shrinks as functions are called and return. And finally, the heap.
Where malloc and new get memory from.
Precisely. The heap is for dynamically allocated memory you request explicitly during runtime and need to release explicitly later, free or delete.
And the heap has its own issues like fragmentation.
Yes. HYDE explains the potential for memory fragmentation on the heap. Over time, as you allocate and free blocks of different sizes, the free memory on the heap can get broken up into lots of small, non-contiguous chunks.
So you might have enough total free memory, but not a single large enough block for a new request.
Exactly. That's external fragmentation. There's also internal fragmentation, where an allocator might give you a slightly larger block than you asked for, wasting the extra space within that block. He also mentions the overhead associated with heap allocation. The memory manager needs some extra data itself to keep track of free blocks, block sizes, etc. It's not free.
Right. Finally, in this memory section, HYDE covers addressing modes. How the CPU actually specifies memory locations.
Yep. Different ways an instruction can say, get data from here or put data there. Direct addressing uses a fixed memory address hard-coded in the instruction itself.
Simple, but inflexible.
Right. Indirect addressing uses a register that holds the memory address. The instruction says, go look in register X to find the address.
Like a pointer.
Exactly like a pointer. And indexed addressing combines a base address, maybe in a register or fixed, with an offset value from another register. This is perfect for accessing array elements.
Yep. The
base address is the start of the array, and the index register holds the element number times element size.
Makes sense.
He even touches on scaled index addressing, common on byte 86, where the index register is automatically multiplied by a scale factor, like 1, 2, 4, or 8, before being added to the base. Super useful for arrays of bytes, words, etc.
And he used that simple example, M1 equals 0, MM1 equals 100.
Yeah, that's a great little illustration. M1 puts 0 into memory location 1, then MM1 equals 100, reads the value from location 1, which is 0, uses that as an address, and stores 100 into memory location 0.
Line denting.
It perfectly illustrates the fundamental idea behind pointers, a memory location whose value is interpreted as the address of another memory location. It's absolutely crucial, underpinning so much of modern programming.
It truly is fundamental. Wow. Okay, so all that lays the groundwork for how we structure our data in more complex ways. And that leads us nicely into the next topic, composite data types.
Exactly. Arrays, structures, objects, building blocks for our programs.
Right. We've talked about individual numbers and characters, but most programs deal with collections of them. HYDE starts with arrays. Those fundamental data structures where you have a collection of elements, all of the same type, accessed using an index, like myArray5.
Yep. And the key assumption, usually, is that these elements are stored in contiguous memory locations, one right after the other. No gaps, except maybe padding for the whole array.
Okay.
HYDE touches on array declaration syntax in various languages. C, Pascal, Swift are mentioned. He explains how they're represented in memory and how the total storage is calculated. Just the number of elements times the size of each element. plus potentially some padding added by the compiler for alignment of the whole array or its element.
Makes sense. Then he discusses multidimensional arrays, like matrices.
Yeah, like my matrix row column. He explains how these are typically laid out in memory using either row major or column major ordering.
What's the difference?
Row major order, common in CC++Rs, stores all elements of the first row consecutively, then all elements of the second row, and so on. Column major, common in Fortran, stores all elements of the first column consecutively, then the second column, etc.
So the linearization in memory is different.
Completely different. HYDE provides the formulas for calculating the memory offset of a specific element typo based on which ordering is used. It's important to know which ordering your language uses, especially if you're passing arrays between different languages or systems.
Good point.
He also points out that some languages, like Swift, might implement multidimensional arrays differently, maybe as arrays of arrays, often involving descriptor objects that hold metadata like dimensions and pointers to the subarrays. More overhead, perhaps, but more flexible.
Okay. Then we move from arrays, same type, to records or structures, different types.
Right. Records or structs in CC++R are collections of data items called fields, which can be of potentially different types, like a struct employee having an integer ID, a string name, a float salary. Hy explains how the fields of a record are laid out in memory, typically in the order they're declared. And he re-emphasizes the concept of memory alignment and padding here. The compiler might insert gaps between fields to ensure each field starts on an optimal address boundary for performance.
So a struct might take up more memory than the sum of its parts.
Often, yes. Due to padding. He revisits unions in this context too, reminding us they allow different fields to overlap in the same memory space. Flexible, but needs careful management.
Right. And then we get to classes and objects, the heart of object-oriented programming.
Yep. Hy explains how objects bundle together both data, fields, attributes, instance variables, and behavior, methods, functions that operate on that data.
Encapsulation.
Encapsulation, yeah. He introduces the concept of virtual method tables, or VMTs. These are crucial for implementing polymorphism.
Polymorphism.
Yeah.
The ability for different objects to respond to the same message differently.
Exactly, like having a shape-based class with a draw method and derived classes, circle and square, each implement draw their own way. If you have a pointer to a shape, the VMT allows the program to call the correct draw method at runtime the circles draw or the squares draw based on the object's actual type.
How did the EMT do that?
Well, simplified, each class with virtual methods has a VMT, which is basically an array of pointers to its method implementations. Each object of that class contains a hidden pointer to its class's VMT. When you make a virtual call through an object pointer, the program follows the object's VMT pointer and then looks up the correct method pointer in the table using an index associated with that method.
Clever indirection.
It is. He also discusses object creation constructors and the common pattern where a derived class constructor needs to explicitly call the constructor of its base classes to initialize the inherited parts of the object properly.
Makes sense. You need to build the whole thing.
Right. HYDE briefly touches on abstract methods, methods declared but not implemented in a base class, and abstract base classes, classes with abstract methods that cannot be instantiated directly. They act as templates or contracts, forcing derived classes to provide their own implementations.
Okay.
And for those familiar with C++li, he mentions the access specifiers private, protected, and public for encapsulation. Though he notes their focus is really more on software engineering principles controlling access rather than the underlying memory implementation, which is the book's main focus.
Got it. Finally, in this composite type section, he talks about protocols or interfaces.
Yeah, using Swift as an example. Protocols, like interfaces in Java or C#, define a blueprint of methods, properties, or other requirements. Classes or structs can then conform to a protocol, guaranteeing they implement those requirements.
So it's another way to achieve polymorphism without inheritance.
Exactly. It allows you to define contracts or capabilities that different unrelated types can adhere to. Very powerful for flexible system design.
Okay, we're getting closer to the bare metal now. Let's talk about Boolean logic and its fundamental connection to digital design. This is really where software meets hardware.
Absolutely. HYDE provides a concise introduction to Boolean algebra, the math of logic, basically. He explains the basic operators, AND or R and not, and how they work with binary values, true, false, 10.
The foundation.
The absolute foundation.
Yeah.
He then introduces truth tables as a way to systematically show the output of any Boolean function for all possible combinations of its inputs. A truth table is the complete definition of a logical operation.
Okay.
He also touches on minterms. A minterm is a product term, an AND of variables, where every input variable appears exactly once, either in its true form or complemented, not TED.
Okay. Why are they useful?
Because any Boolean function can be expressed in a standard canonical form called the sum of minterms form. You basically OR R together all the minterms that correspond to the input combinations where the function's output should be true, or 1.
A standard way to write any function.
Exactly. HYDE also briefly mentions truth maps, also known as Karnaugh maps or K-maps. These are a visual tool used to simplify Boolean expressions. Simplifying is crucial for designing efficient digital circuits with fewer components.
Right. Less gates means cheaper, faster, less power.
Precisely. And here's where the abstract becomes concrete. Highlights the direct relationship between Boolean logic and digital circuits. These Boolean operators, AND, or NOT, are directly implemented by physical logic gates in hardware.
The building blocks.
The fundamental building blocks. He gives the example of decoders. A decoder is a circuit that takes a binary input, like a memory address, and activates exactly one of its output lines based on that input value. It's built from logic gates and is a direct application of Boolean logic used everywhere in computers, like for selecting memory chips or I/O devices.
Cool.
Finally, in this section, he introduces flip-flops, specifically the D flip-flop. These are basic memory elements that can store a single bit of information, a 0 or a 1, and hold it stable.
The simplest form of memory.
Pretty much the simplest sequential logic element, yeah. He shows how they can be built from basic logic gates, and crucially, how multiple D flip-flops can be combined, clocked together to form registers.
Ah, so registers inside the CPU are just collections of flip-flops.
Fundamentally, yes. Registers that hold multi-bit values, like your instruction pointer or general-purpose data registers, are built from these simple one-bit storage elements. It's fascinating to see how logic gates combine to create memory.
It really is. And these registers are key components within the CPU itself, which brings us to CPU architecture and instruction sets.
Right, the brain of the operation. HYDE starts by contrasting early computers, where programs were literally hardwired, with modern stored program computers that execute instructions fetched from memory, a huge conceptual leap.
Von Neumann architecture, basically.
Essentially, yeah. He then describes the basic fetch, decode, execute cycle that pretty much every CPU follows endlessly.
Fetch, decode, execute, repeat.
That's the rhythm. Fetch an instruction from memory, using the address in the program counter. Decode it to figure out what operation it specifies and what data it needs. Then execute that operation, maybe involving the ALU or moving data between registers and memory. Then increment the program counter and repeat.
Okay. And what are the main parts inside the CPU doing this?
He mentions the key components. The arithmetic logic unit, the ALU, that's the calculator, doing math, add, subtract, and logic, AND or compare. The control unit, that's the manager, orchestrating the fetch, decode, execute cycle, telling the ALU what to do, managing data flow, registers those fast, small storage spots right on the CPU chip for holding the current instruction, data operands, results, the program counter, etc. And the bus interface unit, or BIU, that handles talking to the outside world, fetching instructions and data from memory or cache over the system bus.
Got it. Now, modern CPUs are faster than just doing one step at a time, right? Pipelining.
Exactly. To improve performance, modern CPUs use instruction pipelining heavily. HYDE explains how this allows the CPU to overlap the different stages of instruction execution.
Like that assembly line analogy again.
Perfect analogy. While one instruction is in the execute stage, the next instruction can be in the decode stage, and the one after that can be in the fetch stage, all happening concurrently in different parts of the CPU hardware.
So you get much higher throughput. More instructions completed per second.
Significantly higher throughput, yes. Even though each individual instruction still takes multiple clock cycles to go through all stages, you can potentially finish one instruction every clock cycle once the pipeline is full.
And it gets even more complex. Superscalar.
Yeah. Beyond pipelining, there's superscalar operation. This means the CPU has multiple execution units, maybe multiple ALUs, floating point units, etc., and can actually execute multiple instructions completely in parallel during a single clock cycle, provided they are independent and there are enough resources.
Wow.
The 80 by 86 family started doing this with the Pentium processor. HYDE also briefly mentions multiprocessing, having multiple separate CPU cores on a single chip or multiple chips in a system as another way to boost overall performance.
Okay, now, the instructions themselves, they belong to an instruction set architecture, an ISA.
Right. The ISA is the vocabulary the CPU understands. It defines the set of all machine instructions, the data types, the registers, the addressing modes, how memory is organized. It's the contract between the hardware and the lowest level of software.
And Hyde argues even high-level language programmers should care about this.
He does. He emphasizes that understanding the ISA, even conceptually, can be beneficial because every single statement in your high-level language, Python, Java, C++, Y, whatever, ultimately gets compiled or interpreted down into a sequence of these low-level machine instructions.
So knowing what's efficient at the machine level can guide your high-level choices.
Potentially, yes. He gives a simplified example of instruction encoding using a hypothetical y86 architecture just to illustrate the basic idea, how operations and operands are represented as binary codes, as numbers that the CPU's decoder can understand.
And then he dives into the real world with 80 by 86.
Yeah, he delves into some of the complexities of encoding actual 80 by 80 or 8664 instructions. It's a famously complex ISA. He points out how instructions have opcodes that specify the basic operation, but also prefixes that can modify the operation, change operand sizes, specify segment overrides. Lots of historical baggage there.
Sounds messy.
It can be. He explains how addressing modes specifying whether operands are in registers or memory, and how memory addresses are calculated are encoded within the instruction bytes themselves using things like the mod_rm and sib bytes. Understanding this level of detail really does give you an appreciation for what your compiler is doing under the hood when it translates your nice, clean code into this intricate machine language, and maybe, just maybe, helps you write slightly more efficient high-level code by choosing constructs that map well to efficient machine instructions.
Fascinating stuff. Okay, we've touched on memory quite a bit, but Hyde dedicates a whole chapter to memory architecture and organization, going into even more detail. It's clearly vital.
Absolutely vital. He reiterates the purpose of the memory hierarchy, providing the illusion of fast access to a large amount of memory by exploiting that locality of reference we discussed.
Right, keeping frequently used stuff close.
Exactly. He elaborates on the different levels of cache L1, L2, and maybe L3, explaining again how they differ in size and speed. L1 is the smallest and fastest right on the CPU core, often split into instruction and data caches. L2 is larger and a bit slower, maybe shared by a few cores. L3 is larger still and slower, often shared by all cores on the chip.
Okay.
He emphasizes again that when there's a cache miss at one level, the system fetches an entire cache line from the next level down, and the latency involved in going further down the hierarchy, especially to main memory, can significantly impact performance. Hundreds of clock cycles sometimes.
So cache misses are expensive.
Very expensive in terms of time. HYDE revisits the different cache mapping schemes, direct mapped, fully associative, and n-way set associative, reinforcing that they represent trade-offs in hardware complexity versus flexibility in placing memory blocks within the cache, which affects the hit rate.
And he reiterates the benefit of separate data and instruction caches.
Yes, because program code access tends to be very sequential with high spatial locality, while data access patterns can be more varied, sometimes random, sometimes sequential. Separate caches allow optimizing each for its typical workload.
Makes sense. Then he goes deeper into virtual memory and paging.
Yeah, explaining more about the role of the Hardware Memory Management Unit, MMU, and the operating system's page tables. These tables are crucial. They map the virtual addresses used by your program to the actual physical addresses in RAM.
That translation has to happen constantly, right?
For almost every memory access. The MMU, often helped by a special cache called the TLB translation look-aside buffer, handles this translation very quickly most of the time. He describes page faults again, what happens when a program tries to access a virtual page that isn't currently mapped to physical RAM because it's either never been loaded or it's been swapped out to disk.
The OS has to step in.
The OS page fault handler steps in, finds a free frame in RAM, possibly by swapping out another page, loads the required page from disk into that frame, updates the page table, and then lets the program continue execution. The whole process is transparent to the program apart from the delay.
And the analogy of main memory as a cache for disk data.
He really drives that home. RAM acts as a large, usually fully associative cache for the entire address space stored on disk, including program code, data, and swap space. The principles are the same. Locality helps. Misses, page faults are expensive.
And he revisits thrashing too.
Yes, emphasizing again that it occurs when the set of caches a program actively needs, is larger than the available physical memory. The system spends all its time swapping pages in and out, making very little actual progress. A nightmare scenario for performance.
So, more tips for improving memory performance.
He provides further tips, like trying to align your data structures on natural boundaries, word, double word, which can sometimes help cache line usage, although compilers often handle this, and just generally being mindful of access patterns, especially within loops that process large amounts of data. Thinking about cache lines can sometimes guide how you structure your data or loops.
Okay. Finally, in this chapter, he reinforces the different memory sections again.
Yes, code, constant data, static global, initialized and static, uninitialized and BSS, the stack for locals and function calls, and the heap for dynamic allocation. Just providing a more complete picture of how a program's memory is typically laid out and managed by the OS throughout its lifetime.
Got it. Okay, we're nearing the end of our deep dive into the machine itself. Now we need to consider how the computer interacts with the outside world. Input and output, I/O.
Right. Connecting to peripherals, disks, networks, users. HYDE introduces I/O ports as the primary traditional way for the CPU to communicate with external hardware devices.
Ports. Like addresses, but for devices.
Kind of, yeah. On architectures like x86, there's a separate I/O address space, distinct from the memory address space. Instructions like IN and OUT are used to read from or write to these I/O port addresses, which are mapped to registers on the peripheral device controllers.
Okay.
He explains the concept of dual I/O ports, where the same port address might be read only for status information and write only for sending commands or data, and also bidirectional ports that allow data to flow both ways, maybe using separate control signals.
Yeah.
He gives the classic example of the IBM PC Parallel Printer Interface, LPT port.
Ah, the old printer port.
Yeah, it used multiple I/O ports. One for the data byte, one for status signals coming back from the printer, like busy or out of paper, and one for control signals going to the printer, like strobe to tell it data is ready.
Okay. Data transfer rates are obviously important for I/O.
Crucial. Hyde discusses how speed is measured, usually in bits per second, BPS, or bytes per second, BPS. He then introduces system buses, things like PCI, PCI Express, historically ISA, which act as the shared communication pathways connecting the CPU, main memory, and various I/O device controllers. These buses have their own protocols, speeds, and bandwidth capabilities.
And getting devices to talk correctly requires handshaking.
Yes, handshaking is vital, especially for coordinating data transfer between devices that might operate at different speeds, like the CPU and a slower peripheral. It's a protocol of signaling back and forth.
Like the printer port example.
Exactly. The computer puts data on the data port, then pulses the strobe signal. The printer sees the strobe, reads the data, and then signals acknowledge, ACK, when it's ready for more, or maybe signals busy if its internal buffer is full. This prevents data from being sent too fast and getting lost. HYDE provides an 80 by 86 assembly example showing how to check the parallel port status bits.
Okay. Now, how does the CPU know when a device needs attention? Polling versus interrupts.
Right. Two main methods. Polling is the simple way. The CPU just repeatedly checks a status port on the device in a loop, asking, "Are you ready yet? Are you ready yet?"
It sounds inefficient. Wastes CPU time.
Very inefficient, especially if the device is slow or events are infrequent. The CPU spins uselessly. Interrupts are much better. An interrupt is a hardware signal sent from the device to the CPU when the device needs attention. DG, data is ready, an error occurred.
So the device tells the CPU instead of the CPU constantly asking.
Exactly. The CPU can be busy doing other useful work. When an interrupt arrives, the CPU temporarily suspends its current task, saves its state, and jumps to a special piece of code called an interrupt service routine, ISR.
And the ISR handles the device.
Yes. The ISR does whatever is needed, maybe reads data from the device, puts it in a buffer, tells the device it's done, and then returns control back to the interrupted program, which resumes exactly where it left off, usually unaware it was even paused. Much more efficient use of the CPU.
Okay. He also mentions protected mode in modern OCs.
Yes. In modern operating systems running in protected mode, which is basically always these days, direct access to I/O ports and direct handling of interrupts by user application programs is typically forbidden.
Why? Security. Stability.
Both. It prevents buggy or malicious user programs from messing directly with hardware, potentially crashing the system or interfering with other programs. Instead, I/O is managed by the operating system kernel and dedicated software components called device drivers.
Ah, drivers. We've
Yes.
all installed those.
Yep. The driver understands the specifics of a particular piece of hardware and provides a standardized interface for the OS and applications to interact with the device without needing to know the low-level port details or handle interrupts directly. He briefly discusses different driver models and the idea of a device control API for more specialized interactions.
Okay. HYDE then focuses on peripheral buses, especially USB.
Yeah, he briefly mentions older interfaces like SCSI for disks and scanners and fiber channel, high-speed storage networks, for historical context. But the main focus is on USB, the Universal Serial Bus, because it's so ubiquitous now for connecting almost everything: keyboards, mice, printers, external drives, cameras.
Right. Its advantages are?
Big advantages: hot plugging, disconnecting while the system is running, and plug and play, automatic detection and configuration usually. Much easier for users than older ports.
Maybe harder to program for.
He notes that yes, programming USB devices directly is significantly more complex than, say, toggling bits on an old parallel port, because USB involves a much more layered protocol stack. Usually you interact via OS-provided drivers and APIs.
And USB has different ways of sending data.
Yes, he explains the four main types of USB transfers, chosen by the device based on its needs. Control transfers for commands, configuration, status. Bulk transfers for large amounts of data where guaranteed delivery is key but timing isn't critical, like for disk drives. Interrupt transfers for small amounts of timely data like keyboard presses or mouse movements, delivery is guaranteed. And isochronous transfers for streaming real-time data like audio or video where guaranteed bandwidth and timing are crucial, but occasional data loss might be tolerated.
Interesting. Okay, next up, storing all this data long-term. Mass storage devices.
Right. Hard disk drives, HDDs, and solid-state drives, SSDs. He explains the physical structure of a traditional HDD: spinning platters coated with magnetic material divided into concentric tracks, which are further divided into sectors, the smallest writable unit. Read-write heads mounted on an actuator arm move across the platters to access the data.
The moving parts.
The moving parts. He discusses how data is recorded magnetically by changing the orientation of tiny magnetic domains, and mentions bit density, how tightly packed the bits are, which determines the storage capacity. Multi-platter drives stack several disks to increase capacity.
And performance is limited by those moving parts. Seek time, rotation.
Exactly. He defines the key performance metrics for HDDs. Seek time is the time it takes for the actuator arm to move the read-write head to the correct track. There's track-to-track seek time, moving one track over, and average seek time, average time for a random seek. Then there's rotational latency. Once the head is on the right track, you have to wait for the desired sector to spin around underneath it. Average rotational latency is typically half a rotation time. These physical delays dominate HDD access time.
Which is why SSDs are so much faster.
Precisely. He briefly contrasts HDDs with SSDs, which use flash memory chips instead of spinning platters. No moving parts means virtually zero seek time and rotational latency. Access times are dramatically faster, leading to that much snappier user experience for booting up, loading apps, etc.
Huge difference. He also touches on optical media.
Yeah, briefly mentions CD, DVD, Blu-ray technology based on lasers reading pits and lands on a spiral track, and discusses their write-to-write capabilities, CDR, CDRW, etc. And also mentions magnetic tape as a sequential access storage medium. You have to read through it from the beginning. Primarily used these days for large-scale backups and data archival due to its low cost per gigabyte but very slow access.
Okay. Now, just having the storage isn't enough. You need to organize the data. File systems.
Right. How does the OS turn that raw expanse of sectors on a disk into the files and directories we work with? That's the job of the file system and the OS file manager. HYDE explains this abstraction layer. It shields applications from having to deal with physical block numbers and track sector locations directly.
It used to be a thing.
He briefly mentions very early systems, or embedded systems sometimes, where applications might have had to manage physical storage allocation themselves. A nightmare for portability and complexity.
I bet. So how do file systems work? FAT.
He introduces the file allocation table, FAT file system, famous from MS-DOS and early Windows, still used on flash drives sometimes. Its core idea is a table, the FAT, stored near the start of the disk. Each entry in the table corresponds to a block or cluster of blocks on the disk. File entries in the directory point to the first block of the file in the FAT. Each FA entry then either contains the number of the next block in the file or a special marker indicating the end of the file.
Like a linked list scattered across the disk.
Exactly like a linked list of disk blocks. Simple, but it has limitations. Files can become fragmented, their blocks scattered all over the disk, which slows down access because the read head has to jump around. Finding free blocks can also involve scanning the FAT.
So what's better?
He discusses the list of blocks scheme used by more advanced OCs like in NTFS, Windows, APFS, macOS, and Unix-like systems, XT4, etc. Here, the file system maintains information about which blocks belong to which file differently, often using structures like inodes in Unix that contain pointers to the actual data blocks, or extents, pointers to contiguous ranges of blocks. These systems are generally better at managing free space and try harder to allocate files contiguously, reducing fragmentation and improving performance over time.
And HYDE gives advice for writing software that interacts with disks efficiently.
Yes, some good tips. Pre-allocating file space, if you know how big a file will eventually be, can help the OS find a contiguous chunk. Accessing file data sequentially whenever possible is much faster than random access on HDDs. Using buffering, reading, and writing larger chunks of data at a time rather than tiny pieces drastically reduces the overhead of interacting with the OS and the disk. He gives the example of writing an array to a file. Writing the whole array in one go is far better than writing one element at a time in a loop.
Common sense, but good to remember. Finally, to round out the I/O discussion, HYDE covers various specific input-output devices.
Yeah, a few examples. Keyboards. He explains the internal microcontroller, the matrix scanning method used to detect which key is pressed, and the classic problem of key bounce.
Key bounce.
Yeah.
Like pressing a key once registers multiple times.
Exactly. Mechanical switches can physically bounce momentarily when pressed or released, so the keyboard controller needs debouncing logic, either in hardware or firmware, to filter this out and register only a single clean key press.
Okay. Parallel port again.
Revisits the parallel port, emphasizing its use for parallel communication, sending multiple bits at once, and detailing those handshaking signals again, strobe, acknowledge, busy, that coordinate the data transfer with devices like printers.
Game controllers.
Mentions the evolution there. From simple old analog joysticks connected to game ports to modern controllers, often digital, usually connected via USB, these often have their own microcontrollers doing analog to digital conversion internally. And crucially, modern OCs provide standardized APIs, like direct input or X input on Windows, so games don't have to worry about the specific hardware details of each different controller.
Makes game development easier. And sound cards.
Discusses the progression of sound cards, from very basic beeps and boops to early FM synthesis, like old Ad-Lib or Sound Blaster cards, then wavetable synthesis, which used stored samples of real instruments for more realistic sound. And now, modern integrated audio or dedicated sound cards capable of high-quality multi-channel recording and playback, often used for professional audio work.
Quite an evolution there, too. Wow, okay, that was quite a journey.
It really is a comprehensive tour, isn't it? Covering everything from the fundamental binary language all the way up to the complex interactions with the vast array of external peripherals and storage.
Absolutely. So maybe let's try to summarize the key takeaways from this deep dive into Randall HYDE's work. Understanding the machine. What are the absolute must-knows?
Okay, well, first, computers fundamentally operate on binary, zeros and ones. Everything else is built on that.
Right.
Second, they manage memory in a hierarchical way. Registers, cache, RAM, disk balancing speed and capacity using locality of reference. Understanding this hierarchy helps write faster code.
Got it.
Third, characters are represented using encoding standards, primarily ASCII historically, but crucially Unicode today for global text. How these are stored, UTF-8, etc., matters.
Sure. Fourth.
Arithmetic and logical operations happen at the bit level. Understanding bitwise operations, shifting, two's complement. It's the foundation of all computation.
And fifth.
Interaction with the outside world happens through I/O mechanisms, ports, buses, interrupts, drivers, largely managed and abstracted by the operating system.
That covers a lot.
And as HYDE emphasizes throughout the book, understanding these low-level details, even if you never, ever write a line of assembly code, it just provides a much deeper appreciation for how your high-level software actually interacts with the hardware.
Yeah, it's not magic.
It's not magic, and this knowledge can genuinely lead to writing more efficient, more effective, and ultimately great code, like the book title says. It allows you to make more informed decisions about your data structures, your algorithms, how your code might stress the memory system or I/O.
It demystifies things. So here's a final provocative thought for you, the listener, to maybe mull over. Consider how all the layers of abstraction we use every single day in programming, those high-level languages, the powerful frameworks we rely on, the operating systems doing so much behind the scenes, how all of that incredible complexity ultimately rests upon these surprisingly simple yet incredibly powerful fundamental machine operations we just skimmed the surface of.
It's turtles all the way down, in a sense.
Kind of. Maybe this deep dive has sparked your curiosity in a particular area, maybe memory management or I/O or character encoding. We definitely encourage you to explore it further. Thanks for joining us.